Okay, let's do an example. Let's find the vapor pressure of water at 25 degrees centigrade. So we'll use the Clausius-Clapeyron equation. And we're going to solve for the vapor pressure of water at 25 degrees centigrade. So I'll let P2 be at 25 degrees centigrade. Vapor pressure. So I'll bring P1 to the other side of the equation. Okay, so now I know that temperature 2 is 25 degrees centigrade because I've assigned that as being the vapor pressure for that temperature. So I just make sure that my P2, T2 match, my P1, T1 match. So I'm going to solve for P2, the vapor pressure at 25 degrees centigrade. So P2 and T2 have to match. So I need P1 and T1. I'm not given it, but if I'm not given a particular point that I can use, I can always use the normal boiling point, because at the normal boiling point at 100 degrees centigrade, P1, the vapor pressure, has to equal the external pressure, and the normal boiling point is defined as when the vapor pressure is 1 atmosphere. So I can always use the normal boiling point as one of the pressure temperature pairs. So now I've got my two temperatures. I have my P1. I need the enthalpy of vaporization. I can find that in a table, and I can solve for P2. One thing that you want to be aware of are the units, though. So when I plug numbers into this, the P2 is equal to P1, say 1 atmosphere, and then I have times E to the, and I look up the enthalpy of vaporization, that's 44,000 joules per mole. Now I divide by R. This is 8.314 joules per Kelvin per mole. So you'll notice that moles will cancel, joules will cancel here, but my temperature units are in Kelvin. So when I put temperature here, I have to put them in Kelvin so to match the unit in R. So I'll have to put these temperatures in Kelvin. So I'll have T2 is 298 Kelvin, and T1 is 373 Kelvin. Okay, so now I put in numbers, I can calculate the vapor pressure, P2. So for P2, I get 0.028 atmospheres, or that's 21 torr. So the vapor pressure of water at room temperature, 25 degrees centigrade, is about 21 torr, or 0.028 atmospheres. So it's fairly small because water is held together by strong hydrogen bonds.